Hi, I'm Lisa Karam of the National Institute of Standards and Technology and Chairman of CCRI Section 2 on Measurement of Radionuclides. This tutorial is a brief overview of some of the fundamentals of radionuclide metrology. The SI-derived quantity, the becquerel, is the number of radioactive decays per second. Radionuclide metrology, therefore, is all about counting. Radioactivity can be naturally occurring or artificially produced. Both result in natural background radioactivity throughout the world, ranging up to millions of becquerels per kilogram. For example, uranium is about 25 million becquerels per kilogram, while the average adult human is about 100 becquerels per kilogram. Of course, there are many uses of radioactivity in health, environmental studies, industry, and scientific research. Radionuclide metrology, then, is crucial to meet safety and regulatory concerns for the safe and efficient use of radioactive sources, but can be impeded by this natural background. There are some key physics to consider in radionuclide metrology, which are loosely included in what we refer to as nuclear decay data. In addition to the type of energy being measured, such as from photons or from excited particles, half-life, emission probabilities, mode of production, etc. must be known or determined through measurement for the some 200 different radionuclides of interest to the measurement community and stakeholders. The primary modes of radioactive decay to more stable progeny are the alpha, beta minus electron, and beta plus positron energetic particles. Gamma rays usually follow an alpha or beta decay to a higher energy daughter, which then loses energy through photon emission. A special case decay, electron capture, is when an electron from the closest energy level falls into the nucleus, converting a proton to a neutron with the loss of a neutrino. This can be a difficult reaction to follow in metrology. Knowing the half-life or the rate of decay is extremely important. The closer a measurement is made to a reference time t0, the lower the associated uncertainties. This is especially relevant for very short-lived nuclides, such as those used in nuclear medicine. The emitted energy of particles or photons provides key information to identify radionuclides and/or impurities based on their values and their relative yields. Half-lives, energies, emission probabilities, and associated uncertainties continue to be updated by the radionuclide metrology community. Publications are at various sites, especially at the Decay Data Evaluation Project, or DDEP. In radionuclide metrology, primary measurement methods are based on direct detection and measurement of nuclear transitions, independent of emission probabilities, and are generally independent of other radioactivity measurements, calibrations, or standards. They do, however, generally involve assumptions, model dependencies, and corrections. Background, impurities, dead time when too much signal pauses counting, self-absorption of the sample, and ingrowth from the radionuclide being counted or by impurities are all important. Uncertainty budgets must take all of these into account. Choosing the best or even simply a better method also depends on how the source was prepared initially. Decay is randomly occurring, so counts are generally considered equal to the number of events along with a single standard deviation in a Poisson distribution. If the source count rate is close to that of background, which is not uncommon since we try to minimize handling dose by keeping the activity low, then the sample variance is equal to the total variance plus the background variance. Corrections and their uncertainties, such as detector efficiency, self-absorption, and sample density, are applied to the count rate to yield the activity in units of per second, or becquerel. In case you're already aware of the older unit, the curie, note that 1 curie is equal to 3.7 times 10 to the 10 becquerel. No matter what methods are used, certain corrections and issues need to be considered. Physical aspects such as self-shielding, uncertainties on the nuclear data used and their propagation, the activity level, too low will give poor statistics, too high will impact detector response, impurities and complexities of the decay chain, and ingrowth of radioactive daughters, and other factors are taken into account. Calculational approaches and simulations, such as Monte Carlo, often provide a means to address many of these complications and provide a verifiable approach to corrections. The radionuclide metrologist encounters many types of sources, gas, liquid, and solid. Matrices such as soils, building materials, and biologically derived samples can further complicate measurement and generally add to self-absorption issues. In addition, sources may contain multiple radionuclides, including potential impurities. Whether measurements are more appropriate on an intact sample or if radionuclides of interest need to be extracted are also considered in choosing a measurement method. Radioactive impurities, whether occurring naturally or arising from production, present a particular challenge and can interfere with detection or quantification. Using spectroscopic methods such as gamma ray or alpha particle spectrometry can be useful for identification. For some radionuclides, half-life differences can be leveraged over time. For example, letting an impurity die out and then decay correcting back to a starting reference time. In principle, higher count rates reduce statistical errors, but problems arise when the count rate is too high for the instrument. This can lead to inadequate time for the instrument to recover before the next event, poor resolution from overlapping peaks, or peaks that are dropped completely. Dead time, the downtime for signal collection and processing, which is specified for the instrument, can result in a lost peak. Correction of results for counts lost during the analyzer dead time can be overcome by carrying out all counting runs for known or measured total instrument lifetimes, rather than for real time, which remains valid even if the dead time varies widely from pulse to pulse. In metrology, the final result is generally an approximation of the true and generally unknowable answer. It may be exceptionally close to the true answer, but as this is unknowable, the uncertainty may be large. In radionuclide metrology, uncertainty components arise from both statistical and non-statistical estimates, including instrument calibration, reference sources used, decay corrections or half-life, gravimetric mass measurements, lifetime determination, dead time, and detection limits for impurities. High geometry, high efficiency methods assume detection of all decay events in either 4π for 100% efficiency or 2π for 50% efficiency geometries. These methods depend on the ionization capacity of decay or energy transfer with minimal loss. Corrections, though, are still needed. In internal gas counting, radioactive gas sources are mixed with an inert gas carrier, which is ionized by the radiation of decay. The sample is measured in a set of several cylindrical proportional counters of different volumes. The proportional counters are operated in the voltage range under conditions in which the pulse height is proportional to the energy of the original ionizing particle. The result is based on the average of sample results in becquerel per mole among the three counters, while the uncertainty is dominated by that on the mass-dependent pressure. In liquid scintillation counting, a radioactive source is measured in a fluor-doped solvent liquid. Decay energy is transferred to the fluor in the cocktail, which then isotropically releases light detectable by 2 or 3 photomultiplier tubes in coincidence. The technique depends heavily on the physical and statistical model of distribution of scintillation photons and their detection probabilities. Efficiency depends on both the PMTs and on the character of the decay. Counting efficiency is also impacted by quenching, which can arise from chemical scavenging in the sample, light attenuation, and ionization-induced high ionization density. Activity concentration is calculated based on count rate, counting efficiency, and sample mass. More than 50 radionuclides have been measured by the efficiency tracing, usually with tritium, technique known as NIST, after the originating laboratories, including relatively low activity, naturally occurring radionuclides, such as potassium-40. The efficiency calculation is done for a system with 2 PMTs in coincidence of an interaction scintillating photons within the PMTs. This technique has proven particularly useful for half-life determinations if the scintillant is stable. Because the relative standard uncertainty on tritium activity standards can be high, lower uncertainty activity standards, such as manganese 54, may be used as tracers. A 3 PMT liquid scintillation counting technique, the triple to double coincidence ratio method, allows observation of double and triple coincidences, the near simultaneous detection of light signal from a single event using coincidence logic electronics. Although this is a direct method, decay scheme data are absolutely needed for detection efficiency calculations. The activity determination requires a series of paired measurements at different quenching levels. Once the double and triple coincidences are observed, counting efficiencies can be calculated based on published counting probabilities. As the counting efficiency approaches unity, the double and triple coincidence counting rates will both approach the disintegration rate of the source, which will then lead to the activity. Particularly for solid alpha particle emitting sources, the defined solid angle technique, which is below 2 pi, has proven to be a critical metrology tool. Capturing radiation emitted into the solid angle subtended by a scintillation counter and presupposing isotropic emissions and 100% detector efficiency, the approach essentially collimates the radiation to avoid most issues with backscatter. Of course, the thicker the source, the more likely backscatter will become more of a problem. The full energy of the alpha particles is absorbed in the scintillator, and a spectrum of alpha particle counts in a counting period versus alpha particle energy deposited in the scintillator is collected and displayed in a multi-channel analyzer. Overall counting rates are determined from sums of all or parts of these spectra, and the activity is determined from the integrated sums from the resulting spectra. As is usually the case, counting statistics, lifetime, and dead time losses are the significant sources of uncertainties, while the counter geometry itself is considerably less significant. Coincidence and relatedly anti-coincidence methods are applied when two distinguishable radiations, typically gamma emissions following alpha or beta particle or electron capture decay, are in or near coincidence. They are very dependent on the decay scheme of a radionuclide. High efficiency is less important than in the geometry-based approaches, since this is based on the relative chance of a detection of coincidence of simultaneous events compared to the detection of a single event. Additional considerations are needed for accidental coincidence, non-ideal behavior of detectors, angular correlations of the detectors, decay scheme problems, etc. A conventional system, such as that at the NIST, consists of a 4 pi proportional counter coupled to a pair of sodium iodide crystals for sensitive photon detection. The coincidence channel records an event only when it is detected by both beta and gamma channels. A crucial aspect is determining when a pulse occurs, which can be done using pulses directly from the detector or more slowly relying on energy dependence, noting the pulse only when it is a specific energy. The anti-coincidence variant is very much the same setup, with the coincidence channel modified by using the dead time in the beta channel as a count filter to detect only the non-correlated gamma events. In other words, those occurring outside the interval to be considered as coincident with the beta decay. Of course, there are other methods that address special cases and situations, including when the decay scheme is particularly complicated, such as for delayed daughter, as well as normal cases. improvements in such as high efficiency approaches and in TDCR, and secondary methods like gamma ray spectrometry and ionization chamber measurements are all critical in radionuclide metrology, and all depend on some approach to counting disintegrations or particles. Complicated matrices such as building materials or biological samples require special approaches to be addressed, including sample preparation and alternative techniques of measurement. Digital counting has expanded the ability to apply different analysis models and measurement parameters to the same data set to improve results and estimate uncertainties. CCRI Section 2 has developed a Measurement Methods Matrix, or MMM, as an approach to optimizing comparisons in primary methods for radionuclides that can be used to support a wide range of matrices, secondary methods, additional detector types, and a variety of technical modes, such as sum counting, coincidence and anti-coincidence counting with efficiency tracing, and selective sampling. Radionuclide metrology is the optimization of counting a sample which is vanishing and quantifying without counting what should not be counted. Thank you for listening to this tutorial, and please refer to the accompanying PDF for further details.